Welcome to the video on CNC machining a triple droplet generator chip using multiple G-code files and tool changes. Here's a quick overview on the generic CNC workflow. For an entry-level setup, these steps are manual but important for learning the CNC process. While the physical steps may differ based on the CNC manufacturer, the concepts remain the same. As CNC price increases, different aspects of the process, like the bracketed section, become more automated. I'll begin over the manual steps to show how one can maximize the precision of the entry-level CNC for microfluidics. Now let's take a look at the droplet generator chip I'll be machining. Design encompasses different geometries for making droplets. My standard design is a cross-junction with 100 micron width and 100 micron depth, with channels modeled to be 101 micron for the CAM recognition. Check out the previous video on how to set up CAM for more information. For the design to its left, I have a T-Junction, also 100 micron width and 100 micron depth. And the design on the far right has a pseudo T-Junction, but instead of using a 100 micron end mill to define the junction width, I'm relying on the intersection and circular profile of the 300 micron end mill to define the T-Junction. These other channels made using my 300 micron end mill are 500 or 600 micron width. I've made the larger channels 200 microns deep to ensure they're cut because I know my CNC bed is not perfectly flat. Now let's go to the manufacturing tab to see how the CAM is set up. Reference speed and feeds can be found on our website. In total, I have 7 G-code files. 2 files for my 100 micron end mill, 3 files for my 300 micron end mill, 1 for my 1mm drill, and 1 for my 1/8 end mill to cut the chip file. Again, I know the Z depth or flatness is not uniform across my entire XY plane, so instead of configuring features that share the same tool into a single file, I've separated them up into different files so I can re-zero my Z-axes where I want to machine my features. I've also orientated the stock model so the longest channels are machined parallel in the Y-axes. First, I'll use the 100 micron end mill to machine the cross-junction, and come over and machine the microchannel for the T-junction to its left. Since I'm already positioned at this T-junction, I'll go ahead and do the tool change to my 300 micron end mill to machine the 500 micron width channels. The primary reason I'm using a 300 micron end mill is because I didn't buy a 500 micron end mill. After machining the main fluid junctions for this T-junction, I'll use the same tool to machine the primary channels at the center then the primary channels at the pseudo T-junction to its right. The junction intersection being defined by the tool path of the 300 micron end mill. Finally, to finish out, I have 1 G-code for the drill bit and then 1 final G-code to cut the profile of my chip. Now let's go ahead and mount my workpiece onto my bed. In a previous video, I had a wooden spoil board, but it was contributing to the non-uniform flatness of my XY plane, so I replaced it with a machined 4x4 steel block. Instead of gluing the block directly to the bed, there's a layer of tape on the bed and also a layer of tape on the back of the block. On top of the metal block, I've also secured a piece of acrylic as my sacrificial layer, so I can cut entirely through my workpiece. I'll also be mounting my stock acrylic using some tape and glue. Now to mount my acrylic on the machine, I want to position my stock so the machining area is fully supported by the metal block. I'm also not directly aligning onto my sacrificial acrylic because I can use the leftover acrylic on the right to make another chip, and also helps with making it easier to remove. From lessons learned, I'm going to apply a lot of glue, place my acrylic on top, and then give it a good spread so the entire back surface is wetted with glue. Once I've confirmed it's fully wetted, I'm going to hold it firmly in place so I can push out any excess glue from underneath the stock workpiece. While waiting for the glue to fully clear, I can go ahead and set my work coordinates, which is to click the 0xy button in the controller. Setting the work coordinate defines where the part will be made. So what I want to do is jog or move my spindle so it's centered with my 4x4 block, and then click 0xy. Rather than waiting by eye, I'm going to first use the offline keypad to jog the spindle into view. If I didn't have the offline keypad, I'd be using the arrows in the controller instead. Once I've jogged the spindle into view, I load my contour profile and press 0xy to sync the spindle with the controller. Because I can't see the center of my 4x4 block, I bring the spindle to the bottom left as a reference point and hit 0xy. With the controller, I do my final alignment by jogging to the right and up to set my final work coordinates close to the center of my 4x4 block, and finally click the 0xy one last time. I note down these coordinates because if there's ever an error where the machine loses work coordinates, I can always jog the spindle back to these coordinates to this position and try and pick back up where I left off. It doesn't matter what tool is attached including the steps, as long as I remember to change the tool before machining my first spot. With the work coordinate set, it's important to never click 0xy again until I'm done machining all my files, otherwise all the features will be misaligned. Now I'm going to remove the plastic or the craft glue that's protecting the surface of my acrylic, and then I'm going to change my tool. To remove the protective paper right when I'm about to cut so I'm not getting any debris or contamination onto the surface. It might be a little tricky to peel off when it's already mounted, but it helps keep the surface clean. When removing, I'm using one hand to hold down the acrylic so I'm not pulling on the entire workpiece, just in case the glue hasn't fully cured. Once the paper is fully removed, let's jog the spindle up, being careful not to hit the limit switches on the z-axis so I can change my tool. We'll want to be very careful not to accidentally catch the end mill on my glove, because any force may break the spindle. Once it's inserted, I secure the nut to hold it in place, then tighten with my wrenches. To zero my z-axis, I'm going to hold a piece of paper flat on the workpiece, and very carefully, incrementally bring down the spindle until I feel very light scratching on the paper. Making sure the paper is held flat on the workpiece by holding it taut with 2 fingers while applying as little force as possible onto it. Just being very careful to checking how close the mill is to the paper. When moving the paper, it's important to use as little force and movement as possible, just enough to notice if and when the end mill begins scratching. And as the end mill gets closer, it's really important to reduce the step size. And once I feel the scratching, I can go ahead and click 0 to set my z-axis 0. I can go ahead and bring the spindle up, remove the paper, and then hit send to begin cutting. For this particular CNC, I like to hit abort once it's done cutting so the CNC doesn't return back to its home position. Now let's repeat this process for the T-Junction channel to the left. I'm going to jog my spindle over to the machining surface displayed in the controller, then reset my z-axis 0 point. We take a look at my new 0 z-axis reference point. We can see that it's more than 100 micron deviation from my initial, where I machined my cross junction. From the lack of debris, it didn't look like it was cutting, but at the same time, this channel pattern is smaller, so I just wanted to quickly check my G-code and CAM that everything was configured properly. And since everything is okay, let's go ahead and move on to 300 micron end mill to machine my larger fluid channels. Since I'm already positioned on this T-junction, I'll go ahead and machine these channels first. At this point, it's a matter of personal preference. Let's do the tool change, always being careful where I'm holding the tool. And I'm going to load my G-code file and go ahead and zero my z-axis for this end mill using the same process with the paper. Notice I'm using a brush to wipe away any chips from the tool surface. I'm using the brush, I'm just very gently contacting the end mill to remove any accumulation and not forcefully wiping or brushing away the chips. Ideally, the CNC would have compressed air constantly blowing away any chips, but I'm running low on my canned air and only using the brush when machining the small micro end mills. I noticed there is quite a bit of accumulation that I'm unable to remove, so I stopped the machining process. It looks like there's some plastic acrylic melted onto the end mill. What I'm trying to do now is I'm trying to unscrew the melted acrylic from the end mill instead of replacing the entire end mill boot, but it doesn't seem to be working. These 300 micron end mills I'm using were a little over $2 each and came in a pack of 10, but it looks like they aren't all made equally. Turns out this one might be just dull, so I'm just going to swap it out with one I've cut with before. I'm not too concerned with picking back up where I left off because I cut it early enough and the affected channel being cut was for bulk water delivery. What happened to the channel is it ends up being a little bit deeper and wider, which is not too big of a deal for me. So I'll go ahead and just replace the end mill and continue machining. When redoing the full tool change, I'm going to remember to re-zero my z-axis again because the lengths of the tools and how far I insert it may be a little bit different. Once the left channels are machined, I'll repeat the process for the center channels and then finally for the channels on the right. Once it's done cutting, load the next file, reset to 0, and then press send. And then repeat until all files are cut for the same tool. Again, instead of dividing up the drill bit files, they're combined into a single file. I'm okay with deviation and hold depth because if the holes are made too deep, I have a sacrificial layer behind it. And if the holes aren't cutting all the way through, I can manually open up the holes using the drill bit later on. And finally, I'm on to my last file. Going to insert my 1/8 end mill so I can cut my profile to get my final chip contour. But I'm also not too concerned with the variation in depth, since I can always manually post-process. To help remove excess spurs, I've set this one to perform 2 passes. The second pass is identical in depth as the first one, but will help remove any acrylic chips that are stuck to the edges of my final perimeter. If I didn't do this, again, these can also be removed during cleaning. Before removing the workpiece or the final chip, it's important to clean the debris and do one quick inspection. If there are any channels that are not cut, this is the time to go back and attempt to recut them. Once the part is removed, it's difficult to realign and salvage any channels that need to be recut. And if everything looks fine, I can go ahead and remove my chip. I'm going to pop this out and then remove any excess chips that are still hanging off the edges. Now, all that's left is to do a quick cleaning and then assemble for testing later on. Thanks for watching, and let us know if you have questions below. Or feel free to visit our website or blog and check out our other videos where we design and CAM our files.